Now. So, as I was saying, so we have, so a function of two variables essentially means a table like this, right? Clear? Where the row headings, so these are your row headings. These are the elements from the first component. The column headings are the elements from the second component, and the table values are the values that the function gives to each pair. Okay, so that's how we have a record. We have a data table or a function. Now, if you fix A, or for each fixed x, for instance, so you fix x equals 1. The moment you fix x equals 1, the first row gives you a function from A to Z. It takes A to 5, B to 7, C to 96. If you fix x equals 2, it gives another function. So this is your function, which I am denoting by 1, and as if this blank sign means fill in the blank. Okay, so that is my picture, and here it is 2. So both are functions from A to Z. Obviously, you can see that these two functions have the same domain and codomain, but they are different from the values that have been given. And how is it defined? Well, f1 at A is 5, so which is f1a, right? So f1 at A, or f1, so instead of writing like this, as if this should have been the right way, that is how we were writing, this is nothing else but f1. So you see, as if the notation which is fill in the blanks, so that is being used. Okay, all right. So similarly over here, if you fix a column, you similarly get functions. You get 3 functions. So for say y equals A, you have a function from x to z. For y equals B, you have a function from x to z. For y equals C, you have a function again from x to z. Okay? So that's how you see there are. So you see now there are 6 functions. Okay? There are 6 functions. One says you fix your row, or one says you fix your column. And the greatest observation over here is f1, this evaluated at A is same as, say, A evaluated at 1. Okay, and both of them are same as F1A. So that is the meaning by saying that functions of two variables, which is essentially tables like this, are nothing else but actually trying to give you a picture like this. It is some functions and evaluations. So this is A, and you can think of x as if being replaced by this function. So think of x as being replaced by f1 blank, f2 blank, as if. Okay, so that is, so f1 blank, so as if I'm trying to say that this is nothing else but f1 blank A, f1 blank B. So that's the set looking like, as if I'm saying, it's not exactly, and that part is given by that map. Now let us see. So now I will utilize this to say I have a map from x to z to the power a. What is it? I take 1 to f. So that's what I meant by as if. And I will take 2 to this function. So this is my function f star. So now you see, you have this evaluation. You had this map, you had this function, and now this is my f star. So remember, what is f star doing? Well, it takes xa. So for instance, it takes xa, it takes it to this pair f. That's what I was saying. As if you replaced x, the elements x, by this function, and then evaluates this function at this, and lo and behold, what is this? This is nothing else but your f. Okay, so that is so this is, in this particular example, this is how you get this theorem 5.9. Given any function from x to a, there exists a unique function. Oh, sorry, this one I have in this notes I have made this f. This was g over here. So if you read this as f, there exists a unique function f star from x to this, such that this commutes. Okay? So in general, you know now how to create this and write down the proof. Okay? Is it clear now?
Yes, Doc, it's clear now.
Okay. So I hope you will be doing this example 9 as much as you can. Now, before I come to 10 and 11, which are a little bit more involved, and I don't say you should leave it, we should come back. We will in fact come back, and later on we will need them. So we will come back to it. So I was suggesting let's go on. Let's carry on. We carry on with the next section, which is 5.1. Okay, surjections. So do you have the notes with you?
Yes, Doc, we have.
Okay, so if you open your this part, before I come, sorry, before I come to this one, I'm quite tempted to carry on with this example a little more. And the reason is I get a little bit tempted here. Do you remember them? Laws of indices?
Yes, we do remember.
What is it?
Yes, Doc.
What is it?
X to the power A
X to the power A?
multiply.
Yes?
No. Multiply x to the power B
Okay. This is equal
is equal to
Yes?
x A plus B.
Okay. Then?
I think we can give the Charles and Stanley.
Yes.
X to the power minus 1
Okay.
enclosed n
Yes.
equals to x to the power minus n.
All right, but there is much more than this. This is a special case that you told me.
Yeah.
What is the more general one?
X to the power A divided by x to the power B.
Not. You don't need.
Or for that one.
Yeah.
Okay.
So this is x to the power AB.
AB. Yes.
Right, and another one. Anything else?
We talk of the division of x to the power A and x to the power B.
No, division comes the moment one of them is negative.
Negative.
Okay.
And the other one is x to the power 0 is 1. And 1 to the power, sorry. Now all of these rules hold for x is a positive real number and a, b are any real numbers, right? Okay? Correct?
Yes, correct.
Okay.
Correct.
It turns out that with the symbol that we gave, so remember this is the set of all functions. There is another one, obviously, we forgot. Right? xy to the power a is x to the power a times y to the power a, right? That's also there.
Yes. Yes.
Now, with all of them, all these rules hold. That means now what, instead of equality, I'll have a curved equality. And obviously another one was x to the power 1 was x. Now this is the 1-point set. And this is the empty set. This is exactly 1. Now what is this? This means bijective, and that is what we are going to learn now. Bijective or one-to-one correspondence. So the idea is very, very simple, and I don't know if you have seen this beautiful book, The Art of Counting. Without counting. It's a beautiful book, but it lays down the very, very basics. Even people whom we say are illiterate, right? They know nothing. The very, very old, say, tribesmen, they did not know 1, 2, 3, 4, blah, blah, blah. But still had herds and herds of sheep, and yet could maintain it. Well, for each sheep, they had a pebble. I'm not a very good artist. For each sheep, they had a table, and so on. So, someday, if one of the sheep was missing, so they would know that one or few sheep is missing. And someday, if there were more pebbles, there were less pebbles and more sheep, they knew that there's no pebble, so somebody else's sheep has come into his. So what was he doing? He was thinking of a function which corresponds each sheep with a pebble. And that's exactly what we do when we count. We have our standard counting chart. 1, 2, 3, 4. And when we count things, we actually make a one-to-one correspondence. And where we stop, we say there are so many things. So you see, this is just a standardized one, a standard background or a standard thing against which you compare. But that is not required. It's essentially this correspondence which matters. So on the level of sets, we are going to say that two sets A and B have the same number of elements if they have a by one-to-one correspondence. B has more elements or A has less elements if the situation was as I drew earlier. So this is something like this one missing, right? In this case we will say that A has less elements than B, and on the other hand, if we had something like this where there are more, we'll say B has more elements than A. And we are, so to make this, all of this formal, or to make this, the notion of bijection, surjection and injection comes into the world just to make this possible, this idea, to make this idea possible, and that's where the next section starts. So let's look into 5.1 now. So this is in fact the diagram on page 28. It is in fact called the stock diagram, or these top things. That means if you look into this, so the one that I drew was, here is a set, say B, here is a set A, and you have these points over here. And you had kind of funnels. Kind of funnels like this. So let me just copy this. Why do I do this? So these elements and sometimes you can have only one. Okay, so this is a general picture of a function. These are often called the stocks or fibers. So if you have, there are certain names. If you take this map to be F, if you take this Y, this is often called F inverse Y. So this is often called F inverse Y, and F inverse Y has several names. I have used the name the set of pre-images. Of F under F under, sorry, of Y under F. There is also another name, stock over Y, or the fiber over Y by F. Okay, so this picture is very, very, if you keep this picture in your mind, this is a typical picture, and the picture is, so evidently whatever function you have, the fact that every element has an image tells you this way you will exhaust all the things over here. So in other words, we learned equivalence relations. So in other words, these fibers are going to partition off your domain. Okay? The fiber is somehow, the fiber of F is going to partition off your domain. Now there can be, so there is nothing left over here. The only thing is in over here. Either there will be nothing left over. So these are the ones which have empty fibers. Either nothing will be left over. So that's one kind of a case. Or there can be something left over, but none of them will be like this. Everyone will be sticks like this. Alright, so that's the other case. So, and the case when it is both, think, nothing is left over, and when it is both is exactly the picture of our one-to-one correspondence. So that's exactly the definition given in definition 5.11. So that's surjective when nothing is left over. So that's number A, 5A. When each one of them are sticks, some may be left over, that's the case in 5B. And when both of these things happening, there's nothing is left over and each one of them are sticks, so it's exactly 5C, which is your, okay. So and then if we look into these sections, section 5.12, I will leave it to you to read, and then we start next time, but you need to read it first. So that's another. If you look into 5.12a, that is this. So everything is a stick, is at most a stick-like thing. If you look into this section in B, see, if you think of this composition as some kind of a multiplication, so as if I am trying to say that G is a left inverse of F, okay, kind of saying it has a left inverse, and this one is kind of saying that if Fu is equal to Fv, then you can cancel off F from the left hand side. So this left cancel, C is often called the left cancellating property. B is called the invertibility, or it's another name, it's often called splitting. So you're as if splitting, breaking your F, right? So that's another way of thinking. But left invertibility is also has a left inverse, or left invertible is also another way to say it. So you see, these are equivalent. It says that, so A implies B, B implies C, and C. So these are three different facets. So f has that stick, at most stick-like structure. So something like this. Something like this. If and only if it has a left inverse and it is left invertible, left cancelable in any equation of this kind. Okay, so these three are yeah.
Excuse me, Doc. Are you
Yes.
writing something because the screen for me is frozen.
Oh no. I was just referring to.
The notes.
Theorem. Yeah, Theorem 5.12.
Okay.
Yeah. So that AB.
Still on that, Doc, why do you call it a left inverse? Is there a right inverse also?
Yes, that's in the next section. So
all right.
Okay, yes, there is. So obviously, f has Let's see. Now herein I have put in another nice aspect, which is this name function, and trying to say this. It's now time that we learn what is, and I'll come to this. You first give it a reading and then we will see. So next one is about where is it? Yeah, this is about this is properties of injective functions. Every bijective function is obviously injective. It's closed under compositions, and if the composite is injective, see, everything is happening on the left. See, here it says it has a left inverse, it is left cancelable, and here also if the composite is injective, then the left one vanishes. So f is also injective. So as if you can erase from the left. Okay, so the composite is injective, then the left one vanishes, the right one is injective. Okay, G composed f. So again another kind of a okay. Now next section is about surjective functions, which is when none of them are actually empty. All the stocks, there is no non-empty stock. Now if you look into Theorem 5.17, that's where your right inverse comes in. So f is, look into 5.17, f is surjective, that is this part where you are saying that it has none of the stocks are empty. So that's what you are saying. Then you are saying that there exists a right inverse now. F composed G is 1B, so as if we are saying it's a right inverse. So as if these identities are working like ones. There are many ones, but as if something, if you think of it in that way. And then if you look into the third one, it says UF is equal to VF implies U is equal to V. That means as if you can erase off F from the right hand side. So it is right cancelable. So surjectivity, having a right inverse or right invertibility and right cancelability are all one and the same thing. Okay. So again I left and then if you look into its properties, 5.19, every bijection is a surjection and its closed composite of surjections is a surjection. And again you see if the composite is surjective, then as if the right hand side moves out. So G is surjective. Okay. And finally the bijection is both of them, and we have so I leave it to you now to, and something more on this. I have given some examples. So if you look into table 3, we will slowly see that these are examples of injective function. But the third one, again, we are going to make this point very clear. I mean to say, clear as we go, that the inclusion functions, remember, when if you have a subset, then you have an inclusion map, right? These are essentially the injective functions. There is no other injective function else than, so this is essentially the example. And it takes several other forms, as you have on the first 2 rows, but these are essentially the whole idea. These are the only ones. If you look into table 4 on page 30, then again the third one is the only one. Essentially, we will show. We will come to see that this is the only one. So you take. So what are surjections? Well, they are precisely the factor maps. So these are often called the factor maps. So you have a set A. What are surjections? It is essentially giving an equivalence relation on A, partitioning that A by that equivalence relation, and taking those equivalence classes. So assigning X to its equivalence class. Think. The moment you have a surjection, there is nothing left on the codomain. So these empty points, as you see on this screen, these empty points are not there. Okay, so these points are no more there. These don't exist. Why do I not cut them? Okay, these don't exist. So it is something like this. This is exactly a surjection. Now you have already partitioned this. Here is the partition. So there is one part of this set. Here is the another part, and here is another part. Right? So now you can see that essentially giving a surjection means you want to partition A into 3 parts. That's it. Converse is obvious, and giving a surjection. So we will come and see that this is the only picture of a surjection possible. And finally, for this one, now this one is a tricky one. Well, it exactly means one-to-one correspondence and so on that we started off with, and there are many, several, and several, and it will be our work to find them out. So essentially, see, the whole goal was to find out sets which are in bijective correspondence, and so that means kind of has the same number of elements, and then we need to find out methods to say, well, what does it mean to have lesser number of elements and bigger number of elements? So lesser number of elements is essentially the injective part of the story, and bigger number of elements is the surjective part of the story, right? And That's how we are. These are the three parts. So injections we will see are the tool. Injections, as I said, we will see that's our tool towards comparing two sets and finding which one is bigger, smaller, and the moment they agree, we have a bijection. And as you read, you will see that I have called something as a natural bijection, and so on. I will not say now, today, because I want you to read first. So, this week's task, section 5.1. Okay? Give it a reading. Give it a reading. And I don't think if I did mention over here after 5.17 I didn't mention it over here. 5.17, this equivalence is a very, very you try it out, you try to find it out, a rough sketch of the proof is given and so on. You draw these pictures and try to have a proof and so on. Try it out. But I'll tell you next day that there is a hidden mystery there. Hidden mystery means it is something which is very, very deep and very deep and very disturbing, but it doesn't appear on the surface. When you are going through the proof, immediately you will not be able to sense it. It takes years of, in fact, for this to be discovered itself, it took years of research to find that there is a problem here. So it's a serious problem, but we will look into it next day. So I will actually stop here and ask you to read this section 1, this 5.1 first, and then we pick up from there. So we will discuss each one of these in detail next time, but I want you to read it first. Questions? Your inputs?
I've got a question.
Yeah.
Can we assume that B, the set B that we've got on the screen, will automatically also be a partition?
Which one?
The set B.
Oh, on the screen. On the screen. Remember.
It's on the screen.
Yeah, remember, I actually removed this. Because I said I was...
Okay.
So, once I have this...
That you can't have a partition.
Yeah.
Okay, so the question is, if we know it is a surjection,
Yes.
then B will also automatically be a partition.
Actually, the partition that I am considering on B is always the smallest. That means each partitioning set has only one element. So I'm partitioning it like this. Okay?
Yeah.
So I'm just partitioning it like this. So every partition has only one element. Always. Whether it has or it doesn't have. So whether an element has or doesn't. I'm always looking at it in this way. Always. So in this partition is very trivial, right? It doesn't give any more information than what was there in B. Right? It's a trivial way to partition. Unless you you have more than one element in one partition, it's not interesting, a partition, right? So yes, so in a sense I'm partitioning B, but in a trivial way. So it's a trivial partition.
Okay.
Yeah. So you see, so you see at one minute. So you see over here, this is another way to look into this equivalence relation business. So here you had a partition. Okay. Now here is another partition. They don't match. Okay. But if you take their, so this is the equivalence relation S, which is partitioning by this color, and this is the equivalence relation. Okay. Now I am saying you take this one, so you take the smaller one, so this is one partition, so the smallest one. So you see, as if we have put a net, right? The first one you put that white nets, and then you put these nets, and now you have smaller partitions, so you have made it smaller. Previously these were, right? You get it? Your partitioning sets are getting smaller, so you're getting finer and finer and finer, right? Yeah?
Yes, yes.
You get it? So, and that is actually the smallest equivalence relation, we'll come to it, which is bigger than Rn. So, the bigger your equivalence relation is, the smaller your partitioning sets will become. So, you can think of it, the bigger your equivalence relation, it means that more things are getting related, so therefore your partitions are going to be getting smaller and smaller and finer and finer and finer, right? Right? So that is the idea. So you see, there is already a duality, because you are making your equivalence relation bigger. That means more and more things are getting equated. Right? What happens? What happens on the partition? That becomes smaller and smaller and smaller. Right? So that's and as on the other end you make your equivalence more or less closer to the diagonal, lesser and lesser trivial, right? The diagonal, when you take the diagonal, the partition is just this one, the one that it has no more information than the set itself. So that's how you can see things, how you can grade your equivalence relations, and vis-a-vis, on the other hand, your partitions. Yeah. So you should have this. You slowly develop this picture that as you make your equivalence relations bigger, so it is getting thicker than the diagonal, more things are getting involved, then the partitions become finer and finer and finer. Okay? Yeah, but Charles, I interrupted with Charles, yes.
Right, you answered me, but because I just wanted to ask to say, since it is partitioning them, does it really mean that those are equivalent classes with only one single element?
Which one, on B, on the side of B, or A?
On the side of B.
Yeah, B, yeah. But since it is the trivial one, the diagonal, I am not considering it. This partition, because it gives me no further information, right? When you are, the whole idea of, what is the idea of partition? You are saying in some sense, as I said, this idea of gluing. So when you are saying that these elements are in some sense the same, what is that sense? You have told they have the same f value, right? So if you cannot tell me, so that means apart from the set B, you have given me some extra information. So when you are giving me a partition, what does it mean? Or an equivalence relation. You are telling me this element is related to this element, is equivalent as an equivalence relation. So that's an extra information that you have given me. Now when the partition is that trivial, that each one has only one member, you have actually not given me any more information than the original set itself. You are saying y is equal to y. Well, what the hell, I know, yes, y is equal to y. I am not mad. Y is equal to y always, yes. So what? No more extra information. But when you say that y and y prime are equivalent, and y prime and z are not equivalent, but z and z prime are equivalent, so that means you have given some more extra information along with the set. And that is what is happening over here when you partition the set A. So you are saying these elements all have the same f value. The f that I have drawn over here. These elements have the same f value. But here this one only has the same f value. That's what you are saying. So that's an extra information that you have given me. So partitions actually give a little more structure, little more information. Here?
Yeah, it's better now.
Okay.
Thank you, Doc.
Okay. So I expect you to come up with some questions in section 5 next time.
Thank you, Doc.
Thank you.
Thank you, Doctor.
Thank you. Keep well.
Thank you, Dr. Bartha.
Thanks. Keep well.
Goodbye to everyone.
Goodbye.
Bye.
Bye.
Goodbye. Bye-bye.